Hi, this is Mr. Smith. Today we're going to be talking about a pretty big topic in differential calculus, optimization. And you usually see this at the end of the curriculum on derivatives after you've learned all the derivative rules. And then you also learn how to find maximums and minimums. And then you learn how to optimize. So essentially all optimization means is you're going to find the maximums or minimums of certain functions. Like you want to minimize the amount of time it takes to do something, or you want to maximize the amount of money in your bank, or I don't know, something along those lines. Okay, but the very first thing you need to do is find an equation for what you want to optimize. And then you're going to maximize it the same way you found the maximums and minimums of other equations that you've already looked at. And you know that just by the first derivative test, that maximums happen where the derivative goes from positive to negative, and minimums happen where the derivative goes from negative to positive. So that's essentially what we're looking for. Where's the derivative changing sign from positive to negative or negative to positive, depending on if you want to maximize or minimize. So here's this problem. It says that you've got a sheet of paper. It's 8.5 inches by 11 inches, pretty standard. You wish to make a box with no top out of it. You're going to cut squares of side length x inches off of each corner and folding the sides up. So down here we got a sheet of paper, 8.5 by 11 inches. We're going to cut out these little squares on each side. And you can see if you cut those out, it's going to look like a big plus sign kind of. And if you fold up the tabs here, it's going to make a box. Kind of look like this. Volume is pretty simple. It's length times width times height. And our goal here is to find out what should x be in order to maximize the volume of our equation. Now, in optimization, the first thing that we really want to do here is recognize that it's optimization. So it's asking us to maximize. That right there lets you know that you're going to find an equation for something, derive it, find the critical numbers, all that good stuff, and then find out where the derivative changes from positive to negative. So we need an equation for what we're trying to maximize. And what we're going to find out here is that the volume of our box is just the length times the width times the height. Now, if we didn't have any restrictions on this thing at all, then we can make as big a box as we wanted. I could go out and get as much material as I wanted to and make a gigantic box. But the problem is we don't have as much material as we want. We have a sheet of paper. Now, what that really means is while we're trying to optimize this equation right here, I call that the optimization equation, we are bounded by the fact that we only have this much paper. And what that does is it causes this restriction, this restraint. I call it that. And the key to doing optimization problems in Calc 1 is figuring out what are you trying to optimize, what are the restraints, what are our bounds. Well, we're bounded by this sheet of paper, and we want to use the restraints here to try to convert our optimization equation into an equation with just one independent variable. Right now we have length, width, and height as our independent variables. I don't want to derive with those variables. There's too many things going on there. It's kind of crazy. What I'd like to do is convert them all into one variable and derive that guy. So here's what we're going to do. We're going to find out the connection between length, width, and height. And that's what I mean by restraint. You can't make length and width as big as you want. Choosing a certain length is automatically going to limit what your width is going to be. So here's what we got going on. Once we choose x, you can see when we fold up these tabs here, each side is going to be x inches tall. So height is really just x. So I'm going to write that here. X is really just the height. Also, once we choose whatever x is, our width here cannot be 8.5 inches anymore. That's not going to be the width of this box. All right, well, I guess width would be this one if we're looking at this sideways. It won't be 11 inches, I guess. Okay. Once you choose x and cut this square off, the width automatically becomes, it used to be 11, but we're taking away x down here and x down here. So the width is going to be, it used to be 11, but we're taking away 2x. And the length, similarly, used to be 8.5 inches, but once we cut this x off, we're going to lose this x and this x on both sides here, right? They're both 8.5, and we're taking away x on both sides. So the length is going to be 8.5. Take away 2x. Now, what this restraint down here allows us to do is it allows us to rewrite our volume equation here, the one we're trying to optimize, in terms of just one variable, namely x. So we're going to rewrite volume, and it's going to be the length, which is 8.5 minus 2x, times the width, which is 11 minus 2x, times the height, which is just x. Now, we want to maximize, we want to find the biggest value. We can start guessing and checking some x values here. For instance, like I said, let's say instead of doing calculus, we just decide to cut off squares of 1 inch. Well, if I cut off 1 inch on each side, using these equations on here, my volume becomes 8.5 minus 2 times 1, which is 6.5, times 11 minus 2 times 1, which is 9, times 1, 58.5 cubic inches. Okay, so you can see the result of picking one x value, x, this is when x equals 1, down here, is going to give us a volume. However, if we pick a different x value, we're going to get a different volume. If we decide to cut off more, instead of cutting off instead of cutting off 1 inch, let's say we cut off 2 inches. Well, now our volume is going to be different. Now it's going to be volume is equal to 8.5 minus 2 inches twice is 4 times 11 minus, again, 4 times the height, which is just x, 2. So the volume, if we choose x to be 2, is going to be 63 inches cubed, as compared to if we let x equal 1, we're going to get 58.5 inches cubed. So you can see whatever x we choose is going to have a direct result on what the volume is going to be of this box. And if you actually do this with a sheet of paper, you can see that. You can cut off an x, find the volume, great. I mean, you don't really have to cut off the x to find the volume of a box, but maybe you want to make a box and keep it somewhere nice. And always remember you this amazing time in your life. So our goal here is not to guess and check, because any old monkey can do that. What we want to do is find out, using calculus, what's going to maximize this volume equation. Well, here's how this works. We know that our volume equation is 11 minus 2x. I switched it up. Doesn't matter. It's multiplication. We're okay. 8.5 minus 2x times x. If you were just given this as a problem before you started talking about optimization, is y equals this thing, and they said find where the maximum is, you could do that. Hopefully you could do that, because you could derive it, find the critical numbers, all that good stuff. And you can also see that this is going to be a cubic equation. You're going to have an x times an x times an x. That's going to be x cubed in there. This is a cubic equation. Also, you can see that it's going to be a cubic equation with a positive leading term, because when we multiply it out, we're negative 2x times negative 2x is positive 4x squared times another x is positive 4x cubed. We could actually even graph this thing fairly easily, because we could just graph the zeros of it. We already know that's factored form. This is all factored out for us. We know it's going to be 0 when either x is 0. So this is not part of optimization. I mean, you can graph it. It always helps you out. But you don't need to do this to solve this question. I'm just showing you what's going on, what this graph's going to look like. When x is 0, it's 0. When x is half of 8.5, it's also going to be 0. Well, that's 4.25. It's going to be like right here, 4.25. And when x is half of 11, 5.5, that's going to be here. Well, since it's a cubic, the graph must look something along these lines. Cool. Well, remember, this number was 4.25, and this number was 5.5 out here. Well, the maximum is going to be in here somewhere, and without really doing much work, we can see it's going to be less than 4.25, but to actually find it, we got to do some calculus. Anyway, you don't need to know what that graph looks like. I'm actually going to get rid of it. I'm just showing you this function will make a graph. There's nothing wrong with that. We're just going to find out where the maximum is by doing what we've been doing this entire time. First derivative test. So, first thing I'm going to do is simplify it, because I don't want to drive with the product rule here. I'm going to multiply all this stuff out. 8.5 times 11. 8 times 11 is, what, 88 times a half. Half of 11 is 5.5. So 88 and 5.5 is 93.5. Cool. That's that times that. 8.5 times 2x is going to be minus 1617x. Okay. 11 times negative 2x is minus 22x. Negative 2x times negative 2x is plus 4x squared. And we got this other x out here. We're going to multiply it in. So when you do that and straighten out the terms, put the leading coefficient first, we're going to get 4x cubed. This should be... Oh, yeah, we're good. Sorry, 17x and 22x is, what, 39? So minus 39x squared plus 93.5x. All right, I want to know, again, this equation here and this equation down here, same exact thing. We just rewrote it. I want to know where the maximum of this equation is, so we're going to derive it with respect to our independent variable. Cool. And we're going to get 12x squared minus 2 times 39 is what? 78x plus 93.5. Now, we can find out where this thing is 0. It's never undefined. We want to find the critical numbers here, essentially. We can find out where this thing is 0 We can do quadratic formula. We can just use a calculator as well. Teachers probably won't let you use a calculator in a question like this. So let me open up my little calculator, dude. And I'm going to graph this, find out where the zeros are, and those are going to be my critical numbers of this derivative once my TI guy opens up. Let's go, Texas Instruments. There we go. So what we want to do here is clear out any functions we got. So I'm going to hit clear. Let me make sure you can see this. And I'm going to enter in the function, which is 12x squared minus 78x plus 93.5. So 12x squared minus 78x plus 93.5. Now when I graph this guy, I want to see where the zeros are. So I want to know where the zeros are. I know x can't be less than 0 because that's the height, so I'm not going to change the x min. The x max can't be more than, I'm just picking a number, 15, because the paper is only 11 inches long, so there's no way we can cut off more than 15 inches. Oh, I just changed the wrong thing, I'm sorry. Get out of there. 0, enter, 15, enter, and we'll count by ones, no problem. And for the y min and max, all I really want to make sure is that I can see where the zeros are. So as long as my y min is negative, we'll say negative 1, and the y max is positive 1, I'm going to be able to see where this thing crosses the x-axis. So we're going to graph it. And you can see there are two zeros, here and here. And if you want a better picture, you can zoom out some. Just I don't know if you're freaking out because you don't have a good picture of this thing. We can go to negative 10, enter to 10, and graph him. There you go. So you can see it's a parabola opening down. We still can't see the bottom, but I mean, again, if you want to see the bottom, we can lower the x minimum to like 25 maybe. All right, we still can't see it, but it's down there. Whatever. There's two zeros. I'm going to go ahead and find them. But remember, let's try out for a second. We want to know there's two zeros. I don't know what they are right now. I'm going to call the first one A, the second one B. If you're looking at this derivative, which is what this graph is here, what we're seeing is that the derivative is going from positive above the x-axis to negative at the first x-intercept, and it's going from negative to positive at the second x-intercept. We want where the derivative is going positive to negative, because that's where a maximum is, where the derivative changes from positive to negative. So that's going to be this first intercept. Again, if you're making your number line here for v prime, you're going to find positive, negative, positive, which means it's increasing here, it's decreasing here, and it's increasing here. A is where the maximum is going to happen. So all I got to do is find out what A is, and that's a graph. So we can do what, second calc, we want to do 0, enter. Left bound, I don't know, we'll say 1. Enter. Right bound, you can see this thing's in between 1 and 2. I'll just say 3. 3, enter, guess, whatever, do your work. There you go, 1.585. So this number here, this is going to equal 0, and the value we're looking for is this one, and the max is going to happen when this is 1 point, I forgot it already, 585. Now, I guarantee you, if you take a sheet of paper and cut a square off and then find the volume, the biggest volume is going to happen when you cut off 1.585. And that's the work that we just showed and did. Okay? We picked a couple values way back here. I picked x equals 1. I got 58.5. I picked x equals 2. And we got 63 inches. Different numbers. That's fine. We want to find the biggest one. So when we plug in 1.585 for x, we're going to get a volume that is bigger than 63 inches. This is going to be the maximum volume. And if you want to find it, we can do it. The volume is going to be, I'm just going to plug in this number here, 1.585. So let's just do it in the calculator. Get out of here. We had 8.5 minus 2 times 1.585. That's the width. Times, let's put parentheses here, 11 minus 2 times 1.585. Cool. Times x, which was 1.585. Enter. The volume is 66.148 when I make x 1.585, and that's the biggest I can make the volume. No matter how much you cut that thing, the biggest volume you're ever going to get out of that piece of paper, 66.148 inches cubed. So, if the question asks for find x that maximizes it, this is the answer. If it said find the maximum volume, it would be, I just deleted that thing out here, I can't remember what it was 68 point something inches cubed. Okay.